Today we're going to look at Taylor series for functions of two variables. Now in first year, you would have looked at Taylor polynomials, Maclaurin polynomials for functions of one variable in Math 1231. So we're going to briefly review what we learnt last year, and then we're going to see how we can extend it to this more general environment of functions of two variables. All right, so let's review very quickly what we know for functions of one variable. First of all, let's motivate the subject. Why did we learn about these Taylor series and Taylor polynomials and Maclaurin series and Maclaurin polynomials? Well, functions that are sort of polynomials that have powers of x are easy to deal with, generally. Okay, they're easy to differentiate. It's easy to differentiate, x plus x squared. And it's also easy to integrate. So if we can develop a technique or a theory for representing some function as a sum of powers of x, possibly an infinite sum, then this is sort of a very easy framework to work within. We know that powers of x are easy to work with. That's the basic idea. Okay? Of course, you may think, well, okay, these are like series, and they're hard to. When you have an infinite sum here, they're series, and most students think they're hard. Well, yeah, they are. But the basic idea is to write some function as a series involving powers of x, or approximate it as with a polynomial. These things are simple to deal with. All right, so let's refresh our memory. What are Taylor series? What are Maclaurin series? Well, suppose we have a function of one variable f, and it has derivatives of all orders, and basically it's infinitely differentiable. And a some point in the interval of the domain of f, and it's an interior point. We define the Taylor series for f about the point a as this infinite sum. Okay, Taylor series. Notice as you go from term to term, the derivative increases, the power around this x minus a increases, and the factorial that you're dividing by increases. Now, a special case of a Taylor series is when a equals 1. A equals 0. Okay? In that case, the boxed representation simplifies, so just remove all the a's, and you'll get the following Maclaurin series. Now, on the left-hand side, we've just used a sigma notation. Now, sigma notation allows us to write sums in a nice compact form. Okay? Now, if I take just a few of the terms, so I don't keep on adding and adding and adding, I get what's known as a Taylor polynomial for f about the point x equals a. A Maclaurin polynomial for f about the point x equals a. All right, so of order, say, n. So it's just basically you're adding up here up until you get to an nth derivative. Okay? And you stop. Can I have a show of hands? Who vaguely remembers those from last year? Okay, who hasn't seen anything like that before? Okay. All right, don't worry if you haven't seen anything like that before. So to compute one of these polynomials, say, these Taylor polynomials, all you do is you calculate the derivatives and then just write it up using this type of representation. Maclaurin. Colin Maclaurin. He is one of the mathematicians who came up with Maclaurin Series, Maclaurin Polynomials. He was a professor of mathematics at Edinburgh, and Isaac Newton actually was so impressed with him that he paid, at least he offered to pay some of Maclaurin's salary. That's pretty good when you're bankrolled by Newton. Okay, it's pretty good. All right, so some basic list of Taylor series. Actually, no, these are Maclaurin series, I beg your pardon. So A equals 0 in all these cases. So you can write e to the x, sine x, cosine x in these infinite series. Now you should, okay, probably the best advice I can give you here with this topic is to learn these type of series. Okay, so you should be able to write down the Maclaurin series for e to the x, just like that, for sine x, for cosine x, for 1 on 1 minus x. Okay. Now you don't have to remember all of these. If you know some of them, you can work out the other ones. So if I know, for example, the series for sine x, how can I get the series for cosine x? Anyone know? Differentiate. If I know the series for 1 on 1 minus x, how would I get this series for 1 on 1 plus x? I know the font's really small. Well, all I would do is replace x with negative x. Okay, and use the formula, the representation from up here. Okay, if I replace x in there with a negative x, I'll get that, and just replace x with negative x in there, and I'll get that. Okay. How can I get the series for this? Well, it's just the integral of that. So if I know that series, I can integrate term by term and get that. Okay, so you don't need to memorize all of these series. You just need to be able to recall the important ones, because then you can derive them if you really need to. And like I said before, if we take a finite number of terms in our series, then we obtain so-called Taylor and Maclaurin polynomials. Now, the important thing about these polynomials is they approximate functions. They can approximate, e to the x or something like that. So what we're going to do today is look at how we can build on this knowledge from last year for functions of two variables. What does it look like for functions of two variables? How do the derivatives work and things like that? So that's one of the goals of this lecture. Now, last year, whether you may not remember this, but Taylor's theorem. Again, we're working with functions of one variable here. Under these conditions, Taylor's theorem says that there is some number c between points A and B, such that this is true. Now, I've said down here Taylor's theorem is an extension of the mean value theorem. Well, if I let me sort of justify that for you. By the way, this was on page 106. I flicked it through to page 105 because it was sort of in the wrong spot. if n equals 0 up here, so basically I cover that and I cover all those, and n equals 0, I actually get the formula involved with the mean value theorem. So let me... Okay, so this will be f of b equals f of a plus this for some c between b and a. It's the MVT. Okay, so Taylor's theorem, as it's stated here, is just a generalisation of the MVT, the mean value theorem from first year. You're just taking more derivatives, essentially. Now, from a practical point of view, this theorem isn't actually that useful. What we're going to do is change b to an x and look at it in that form on the next page. That's going to be slightly more practical from our point of view. Okay, so we basically change b to x in Taylor's formula and we come up with this. Now, this is probably something that you're slightly more familiar with from first year. Essentially, what this slide says is that under certain conditions, a function that has enough derivatives is equal to its Taylor polynomial plus a remainder. And the remainder is denoted by this, and I guess here it is in its full form. Okay, so that's important. To really understand the basics of this theorem and why it's important, I think you really need to appreciate how powerful that theorem is. As long as a function is differentiable enough times, you can always write the function as its Taylor polynomial plus an extra bit, like a remainder factor or an adjustment factor. That's pretty powerful stuff. Okay, so essentially this sort of representation is what I've just said out loud. You can write a function as a polynomial, Taylor polynomial, plus some error term. That's the summary of this theorem. Very powerful. Very powerful. So, how does this work for functions of two variables? That's a little bit about functions of one variable, but this is multivariable calculus, right? Vector calculus. How does it work for functions of two variables? Well, yes, the ideas are very similar, but there's a twist here and there. And the beautiful thing about the derivation for the two-variable case is that it relies on stuff that we've looked at during this particular section. Okay, so suppose I've got a function of two variables, f. I'm going to define the Taylor series expansion, denoted by this t, about the point a comma b. So think of a, b as some point in the domain of f, as the following. Now, note we've got partial derivatives here, and then they keeping, like, the sort of order keeps increasing. Now, I haven't written out the whole series because it's very messy. It gets messy real quick. So I've just sort of signified the rest of the series by this plus ... higher order terms. Now, it turns out that what we'll actually be interested in calculating are the first and second order sort of polynomials. So if I cover that up, and I cover that up, So that's the first order, what's there. That's the second order, that and that. So that's actually what we'll be producing. We'll be producing Taylor polynomials of first order and second order, rather than the series. Okay, so I've defined those on the next page. So T sub 1, T sub 2. So there's a lot of partial derivatives to calculate in there. Now I'm also, I guess, assuming that the mixed partials commute. Okay, that's why I've got this 2f sub xy, not f sub xy plus f sub yx. Okay, so throughout you can assume that whenever you're calculating these Taylor polynomials, the partials do commute. Okay.
Shouldn't the T2 have the first order derivatives as well?
It does.
Oh yeah.
Right. So I've just done that to save a bit of space. Otherwise, it just takes up the whole slide. Yeah. You think? So just to save a bit of space, I've defined T1 in this way as the first order one, and then I've just stuck it in there to save space. Now, you may go, hang on, Chris, these are polynomials, right? Don't you talk about the degree of a polynomial? Well, technically, yes, you should, right? But because derivatives are involved, I like to talk about the order of these Taylor polynomials, okay? Now, just like functions of one variable have these approximative properties with their Taylor polynomials, these two also give approximative, approximations. And in particular, T1 gives what we call first degree approximation to f near the point of interest, and T2 gives second degree approximations. Now, let's try to put this into some sort of context. Does anybody recognise T1, what kind of equation that is? Anyone seen that somewhere before in this course? What do you think T1 might be geometrically? Yes? Not a normal. You're close though. Tangent plane, right. Okay, so T1 is just the equation of a tangent plane to the surface z equals f of x comma y. Okay, so we've sort of already seen the Taylor polynomial of first order already. Okay, in the previous lecture and probably the lecture before that. All right, let's calculate some Taylor polynomials. First, I guess a good question at this stage is, will you get that? That seems like a big mess. Will you get that in the exam? I can't guarantee that you'll get it. Okay? You certainly wouldn't get T1. I haven't decided whether you'll get T2 or not, but I think it's unlikely. Okay? So let's actually solve some problems. Calculate the Taylor polynomial. I guess in this case it's a Maclaurin polynomial because it's about 0, 0. You want to include the quadratic terms about the origin for this function here. So really it's the Maclaurin polynomial. Now, there's a fast way of doing these kind of problems and a slow way. Anyone say for this one? Think about e to the x and sine y multiplied together. If I know the expansion for e to the x and I know the expansion for sine y, I can just multiply the two series together and get the polynomial I want out of that. So this is very typical of a lot of these questions. They actually just rely on what you know from first year. So this is one way of doing it, all right? So I know that e to the x is just 1 plus x squared on 2 plus blah, 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 right? Plus the higher order terms. Okay, I can just write that down. I know that. That's hardwired into my brain. Sin y is a little trickier. Sin y is something like y minus y cubed, that's cubed, on 3 factorial plus y to the 5th on 5 factorial minus blah, 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 blah. Now, we're only looking for those, for the polynomial up to and including the quadratic terms, the squared terms, or the x times y terms. Okay? So what I'm going to do is actually multiply these two things together and then have a look at what terms I sort of want to pick out for my, my polynomial. Now, you might think, hang on, how am I going to multiply that together? Well, the first thing is we are not worried about the series. We're just worried about the first few terms, the polynomial, right? So what I need to do is pick, I guess from a method point of view, what I'm going to do is just pick out the first few terms and sort of look at how I can multiply them and just take the ones I need. So essentially, my polynomial is going to have constants, x's and y's, x squareds and y squareds, and xy. Some of those, nothing else, right? So let's see if I multiply, say, this with this, then I get everything I want. And if I multiply this, say, with anything else, or any other multiplication, is going to give me the higher order terms. Okay? So now I'm just going to pick it's just going to be this times this. Okay, there are no constants to worry about. Yes. So by that, right, what we mean is, we mean the last term should involve something like x squared, y squared, or x times y. Okay? So although it doesn't have powers of 2 in it, you can kind of think of this as being in the quadratic term. Okay? It just turns out that the coefficients for x squared and y squared in this are 0. Yes?
What about the x squared and y?
Well, okay, so why are there no x squareds and y squareds there? Well, you can't. I mean, try to multiply. Try to find an x squared and a y squared out of this multiplication. It can't be done. Okay? So what do you conclude? Well, the coefficient for x squared must be 0. The coefficient for y squared must be 0. So you've got 0x squared plus 0y squared in there. Okay, but you don't have to write that down, of course. Okay? Now, if you're a little bit uncomfortable with that quick method, you can go through and verify that this is actually correct. Okay? So what you would do, you would work out this, all at 0, 0. So you'd have to calculate derivatives for this function, 1, 2, 6 derivatives, including the 0th derivative, and then evaluate them at 0, 0. You can do that. I wouldn't recommend it, but it's up to you. Okay? Sometimes in the exam you might go, oh, I can't remember what's the series for sine again? I can't remember. Okay? You can just plug in the derivatives and evaluate them and then use the formula. There's nothing wrong with that. It just takes time. Yes? Okay, because that's not, technically, what we want to produce is something like this. Okay, so if you look in here, look at the A and B is 0. So you have x squared, xy, something times xy, and something times y squared. You see how there's no x squared y in here? Yeah. So that's what we mean when we say quadratic terms. Maybe it's simpler if I just say, the Taylor polynomial of second order. Maybe that's actually clearer. Okay, so to check the above, you would calculate, if you wanted to, you don't have to, but you have to calculate this, 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 and this. Okay, now a lot of these are 0. So I'll just write them down just from what I've calculated. This is actually 0. This is 0. This is 1. This is 0. That's 0 and that's 1. Okay, but if there's a simple way of doing it, like I believe in part 1, you should take that, or at least seriously consider that option, rather than grinding through it and just. I mean, there are some cases where you won't see a simple option, or a simple option might not be available. Okay, in that case, of course, the default setting would revert you back to calculating these partials. Okay, so I said that these polynomials provide approximations. So let's have a look at, here's our original function. This is our t sub 2. Here, I've basically graphed the difference between the function f and the Taylor polynomial t2 that we just calculated. So you can use a 3D plot. Now, similar to the example from the last lecture, you can see that if I'm in the xy plane and I'm close to the point 0, 0, then that surface isn't too far above or below me. Okay, but if I move away from the origin, say I'm at the point 5, 5, then the surface either is going down or going up. It's moving away from the xy plane. So it means that the error is large. So what does this tell you? It tells you that these polynomials are good approximations, but only if we're close to our point of interest. Okay? Only if we're close to our point of interest. If you move away, then it's not such a good approximation. Now, later in this course, you'll look at approximations that work on intervals, okay, across a whole interval called Fourier series and Fourier polynomials. Okay, it's really important. Okay, so let's do another one. Here we have a function of two variables. Calculate the, I guess again it's a Maclaurin polynomial. So we want t sub 2 here about the origin for this particular function. Now, again, there's There's two ways of doing this problem. Can anyone suggest how we might quickly write down the series associated with this and then just choose the terms we want? There's no multiplication this time, but what happens if I write it like this? Anyone suggest how we might go back to first year and try to write that as a series? Yes. Use the fourth line in that table. Okay, so we know. So I'm just going to say, just put in a U here so we're not confusing our variables. Okay, so of course, I should really be a little bit more careful here. Now, let's just make a substitution. Let's replace u with x plus y. So what will our t sub 2 be? Well, it would just be the first three terms. Okay? It'll just be the first three terms because that last term is going to give us an x squared, a y squared, and a 2xy. Now, if I wanted to expand this out, I could. I'll expand it out. Okay, you don't have to. You can. It's probably prettier to leave it in that form. Now, again, if you can't remember the series for 1 on 1 minus u, you can compute the derivatives of f. Okay, compute all the partials and evaluate them at 0, 0. They'll give you these coefficients. Okay, so I'll leave this for you to do. All right, now I will show you how to do one of these using just the bog standard methods. Okay, so that's the next one. Also a little bit on class test type etiquette here. If we ask you to use the formula, for example, if you look at the next question, what we're actually meaning here is for you to systematically go through and calculate the partials and then apply the identity, I guess, for t sub 2. Okay, so our point of interest is 1, 0. So what I like to do with these things is if I know I'm going to calculate, we'll do a bit of calculation, I form a little table. So I write the derivatives, the general derivatives down one column and the values at the point of interest down the other. So at the point 1, 0, this is going to be log 1, which is just 0. So let's calculate our partials. So we're going to get 2x on x squared plus y squared. So at the point of interest, we're going to get 2 on 1. F sub y is going to be very similar to f sub x, except we've got a y on top. Okay, so if I put in 1, 0, I'll get 0. So now on to the second partials. All right, so to differentiate up here, I can do it a few ways, just maybe using the quotient rule. Okay, if you calculate that, and I'm just sort of working off one I've prepared earlier, you'll get something like this. And then subbing in x equals 1, y equals 0, I should get minus 2. F sub y, so differentiate this. Very similar here, except I've got a change in the top. So if I plug in x equals 1, y equals 0, I'll get positive 2, and then just the mixed. So I want to say calculate this, the derivative of this with respect to y. So I'll get something like this. Okay. So let's put it all together. We've got all these constants down the right-hand column. They're just the coefficients in our polynomial. All right, so the first term's 0. The coefficient of x minus 1 is that. 0 times y minus 0. Okay, and then it's the second order partials. So I'm sort of writing all these zeros and stuff in just to give you sort of, you can look back and see where each bit goes in a more general case. Okay, so all I need to do now is simplify that, and I should get the following. Okay, 0, 0, minus. Now, of course, you might be able to expand those brackets and simplify it, but my advice is you don't have to. Firstly, because it's easier to mark if you had that sort of nice form at the end. Yeah, so I wouldn't spend any time simplifying that if you don't have to. You're not being lazy, in my opinion. Okay. So you can see how to compute all these derivatives, we were asked to compute all these derivatives, but it can take a long time. I did it pretty quickly because I had something prepared. But in a test, that could take you quite a while, right? So the idea is if you look at, say, two functions multiplied together, and you know the series for each function, that's gold. It's just fantastic to be able to do that. Okay. Aha. Taylor's Taylor's theorem for functions of two variables. Now, this looks like a big mess, but essentially, it's very similar to the slide that I showed you for the functions of one variable. What does this say? Well, let's concentrate on the second one, because that's actually probably the more useful one for us. Okay. Under certain conditions, right, which are up here, the second theorem tells you that a function of two variables is equal to its Taylor polynomial, its Maclaurin polynomial, plus a remainder. And the remainder is here. Okay, and this Cx, Cy is some point between the origin and x comma y. So this C here so you've got, let me just sort of draw a little diagram here. Okay, here's the origin. Say here's a point, say x comma y, and you draw a line segment. There's some point on that line segment, oops, Cx, Cy, where you're evaluating this. Now, you may think, what do these things mean? Well, if you look up here, or actually just here's fine, you're just expanding this, like the coefficients, for example, like you would be expanding in Pascal's triangle. Okay? So what they've done there is used a fancy notation. I wouldn't worry too much about it, but essentially what I like to think of this theorem as is just a generalization. It says what you can do for functions of one variable with Taylor's formula, you can do with functions of two variables. Okay? A function of two variables under certain conditions can be written as its Taylor polynomial plus a leftover bit, plus an error term, right? Okay. Now, an important piece of information, if I signify T sub n as the nth order Taylor polynomial, say about, basically Taylor's theorem says, under the conditions of Taylor's theorem, it says that the Taylor polynomial closely approximates f to the nth degree near the origin. So what does that mean? It means that at the origin, the Taylor poly and the f are exact. They're an exact. It's an exact approximation. And secondly, if you think of this as the top as an error between the function and its approximation, well, you have this sort of first degree, nth degree approximation sort of defined by this limit. Okay, so you see we've got the power of n down here, and furthermore, the nth order Taylor polynomial is the only polynomial of nth degree that satisfies these conditions. Okay. So in other words, the Taylor polynomial is the best polynomial of that degree or less that satisfies this. Okay. All right, so let's look at an example and see how we can put this all together. Calculate the first order Taylor polynomial approximation to this function about the origin and prove it's a first degree approximation. Okay, so now in this, the point of this example is to show you how Taylor's theorem sort of comes into the mix and plays a big role. Okay, any ideas on how we can come up with a series for this? That's it. We know the series for e to the x, we know the series for e to the y. Let's just multiply. Okay. So now all I want to do is pick out those terms from that product that give us the first order Taylor polynomial, T sub 1. So what am I going to do here? Any ideas? Which term should I pick out? Yep, 1. What else? Yep. Anything else? No, we don't want the xy because that would be for t sub 2. So that's it, I think, isn't it? I think that's it. Yep. It's pretty easy, right? How good's that? Now the hard bit. Prove that it is a first degree approximation to f. So what I want to do is show that our t sub 1 satisfies these two conditions for n equals 1, because we're asked to prove that it's a first degree approximation. This is nth degree, right? So for n equals 1, we want to show this is true and that this limit's 0 for n equals 1. Right? So let's have a look. So that's part 1, I guess. All right, so let's claim T1 is a first degree. Okay. So firstly, what do we need to check? We need to check that this thing is true for n equals 1. So T1 at 0, 0 is just 1 plus 0 plus 0, 1. What's f at 0, 0? It's e to the 0, which is 1. Okay? So those two values, you get absolute sort of exactness at the origin. Now, consider this. We want to show that this goes to 0 as x and y go to 0. Right? Now, by Taylor's theorem, we can write f of x, comma y, as t1 plus a remainder. Okay? That's what Taylor's theorem says. So, for this one, I'm just going to write out the t1 that we just calculated, and then I know there's some c between 0 and 1, such that f of x, y is equal to this. That's an application of Taylor's theorem. Okay? Taylor's theorem says, I know that there's some c between 0 and 1 such that f is equal to its Taylor polynomial plus some remainder term. That's the remainder term for this particular function. Okay, so that's that minus 1 plus x plus y. So I can cancel off all those terms. Bang, bang. And now all I need to do is look at the limit of this. Any ideas how we might calculate that limit? Well, I'm going to expand the x plus y all squared and then apply, you guessed it, Young's inequality. Okay? So here, I know that 2xy is less than or equal to x squared plus y squared. So at the top, oh, hang on, I'm missing a 2, aren't I? That 2. So at the top, I'm going to get a 2. I can cancel that. I'm going to get x squared plus y squared on the top. So I can simplify. Now, what's that bottom line going to go to as x and y go to 0? Zero. So we will conclude that T sub 1 really is a first degree approximation. Now, can you see how that's used a lot of elements from the rest of this section? Limits, derivatives. One important question is, where does the Taylor polynomial for a function of two variables about a point a comma b, where does it come from? Well, it relies on stuff that we've looked at. It actually relies on the chain rule. So I just wanted to quickly discuss this, and then we'll move on to the new section. Okay. So here, A and B is just the point of interest, the point about which you want to calculate your Taylor polynomial. Now we're going to introduce a new function, big F of t, a function of one variable. And it's going to, essentially you're just sort of changing f to include these tu, a, t, v, and b. Now think of little t as the variable, a and b is the point of interest, and u and v are just being held fixed. Now, because ultimately this is a function of one variable, I can calculate its Taylor polynomial about, say, t equals 0. To do that, we need to compute the derivatives of f and evaluate them at 0. So how can we compute the derivative? Well, we can use a chain rule. Okay? To compute the derivatives of this type of setup, we just use the chain rule. So if you just apply the chain rule and calculate your derivatives and plug in t equals 0, of course, f of 0 is just f of a comma b, right? Big F of 0. Okay, go through, you get the first derivative. You might want to draw the little linking diagram that I've showed you how to draw. I'm not going to do it in this example. Once you've got the first derivative, you can, if you want to, draw another little linking diagram and compute the second derivative by applying the chain rule again. So you've got big F prime of 0, big F double prime of 0. Are you starting to see a little bit of a sort of familiar pattern here when you compare it back with sort of this and this? The only thing that's here that's not on the other page is the u and the v's. Well, we can just replace u with x minus a in brackets and v with y minus b in brackets. So to set up our second order Taylor polynomial for big F of t about 0 is just this. So I know what this is. It's here. I know what this is. I just calculated it down here. And same down the bottom. And just replace u with that, v with that, and hey presto. You get your big, long polynomial. Okay, so that's where it comes from. It's nothing more than applying what you already know from first year, but using the chain rule that we've developed in this course, and that you've kind of seen earlier as well. So that's where it comes from. Now, I wouldn't expect you to be able to derive that in an exam or anything like that. I mean, for my money, I actually just try to remember the format of that bottom sort of expression. And it's not guaranteed that you'll be given that, on a formula sheet or something like that. But I'll let you know either way. So for now, you need to remember it.